Replication means keeping copies of the same data on multiple machines connected over a network. That sounds expensive and complicated, so why do it? The book identifies 3 distinct reasons, and they're worth understanding separately because they lead to different architectural decisions. The first reason is geography. If your users are in New York, Singapore, and London, a single database in Virginia will feel slow to everyone except the New Yorkers. By replicating data to servers in each region, you serve reads from the nearest copy. Latency drops from 200 milliseconds to 20 milliseconds. That's not a minor optimization, it's the difference between a responsive app and a frustrating one. The second reason is fault tolerance. If you have one database and it fails, hardware fault, network partition, software bug, power outage, your entire system is down. With replicas, a failure on one machine means you fail over to another. Your users see nothing. Replication is what lets systems achieve 5 nines availability, 99.999% uptime, less than 5 minutes of downtime per year. The third reason is read throughput. A single database machine can handle a finite number of read requests per second. If your application is read-heavy, a news site, a social feed, an analytics dashboard, you can scale reads horizontally by routing them to replicas. 10 replica machines means 10 times the read capacity. Each of these 3 reasons, latency, availability, throughput, applies different pressure to your replication design. And they come with a challenge that is surprisingly hard to get right. If data is written to one node, how does it get to all the others? Every approach to this question involves trade-offs between consistency, availability, and performance. Chapter 5 of Designing Data-Intensive Applications maps those trade-offs in detail. We start with the simplest and most widely used model, leader-based replication. Leader-based replication, also called master-slave replication or active-passive replication, is the most common approach. It's used by PostgreSQL, MySQL, Oracle DataGuard, SQL Server Always On, MongoDB, RethinkDB, and Espresso. When you use almost any relational database in production, you're almost certainly using this model. Here's how it works. One replica is designated the leader, also called the primary or master. All writes go to the leader first. The leader writes the new data to its local storage and simultaneously sends a replication log, sometimes called a change stream, to all the followers, also called replicas, secondaries, or slaves. Each follower receives the replication log and applies the same writes in the same order as the leader did. The followers' local copies of the database are now updated to reflect the write. When a client wants to read data, it can query either the leader or any of the followers. But writes always go to the leader only. Followers are read-only from the client's perspective. This model works well for many systems because reads typically outnumber writes by a large margin. A news article is written once and read thousands or millions of times. A product listing is created once and viewed by many shoppers. By routing reads to followers, you distribute the read load across many machines while keeping writes serialized through a single point. But the single write point is also the model's central vulnerability. If the leader fails, who takes over? How do you ensure no writes are lost during the transition? How do followers know the leader is down and not just slow? Before we get to those hard questions, we need to understand one choice that profoundly affects the answers. Should replication happen synchronously or asynchronously? Here's a question that sounds simple but has enormous practical consequences. When the leader receives a write, should it wait for followers to confirm they've applied the write before telling the client success? That's the synchronous versus asynchronous replication choice, and it's a direct trade-off between durability and performance. In synchronous replication, the leader waits for a follower to confirm the write before returning success to the client. The client knows that when the write succeeds, at least 2 machines hold the data. If the leader crashes immediately after, the follower has the data and can take over. No data is lost. The cost: if the follower is slow, overloaded, or unreachable due to a network issue, the leader must block, it can't complete any writes until the follower responds. In a fully synchronous system with multiple followers, one slow follower freezes all writes for every client. That's unacceptable in practice. The real-world solution is semi-synchronous. One follower is synchronous, the rest are asynchronous. This guarantees that at least 2 machines always have the current data, the leader plus the synchronous follower, without requiring all followers to be available. If the synchronous follower becomes unavailable, one of the asynchronous followers is promoted to be synchronous. In asynchronous replication, the leader writes locally and immediately returns success, without waiting for any follower. This is fast, writes complete as fast as the leader's local storage. But if the leader fails before the followers have caught up, the unconfirmed writes are lost. The book is direct. This means the write is durable only on one machine at the moment it's acknowledged. If that machine dies before replication, the data is gone, even though the client received a success response. Many systems, including MySQL's default configuration, use asynchronous replication. The speed advantage is significant. The durability risk is real. Most teams choose to accept that risk because failures are rare, and because recovery procedures can usually minimize the data loss window. Follower failure is easy. A follower knows its last applied position in the replication log. When it reconnects after a crash, it requests all changes since that position and catches up. No human intervention required. Leader failure is a completely different problem, and the book spends significant time on it because the common assumption is just elect a new leader. In practice, that process is fragile in ways that aren't obvious until something goes wrong. The automatic failover process has 3 steps: detect that the leader has failed, elect a new leader, and reconfigure clients to send writes to the new leader. Detecting failure sounds simple. Most systems use a timeout. If the leader doesn't respond within 30 seconds, assume it's dead. But what if the leader is just slow because the network is congested? Declare it dead too early, and you trigger an unnecessary failover. Wait too long, and your system is down for 30 seconds every time the leader is genuinely dead. Electing a new leader requires consensus among the remaining nodes. The best candidate is the follower with the most up-to-date replication log, the one that has fallen least behind. But consensus protocols are complex, and we'll cover them properly in Chapter 9. Here's where things get genuinely dangerous. Suppose the old leader had received some writes that weren't yet replicated to any follower before it crashed. A new leader is elected. The old leader recovers and rejoins, it still has those unreplicated writes. Now 2 nodes believe they are authoritative for different versions of the same data. The common solution is to discard the old leader's unreplicated writes. But discarding writes means data loss. Writes the client was told were successful are now gone. In 2012, this exact scenario caused a major incident at GitHub. When a failed MySQL leader rejoined, its stale data was promoted back, causing inconsistencies between MySQL and Redis that exposed private data to the wrong users. The other nightmare scenario is split brain. 2 nodes both believe they are the leader. Both accept writes. Now you have 2 diverging copies of your database with no coordination between them. Some systems have a shoot the other node in the head mechanism, STONF, to ensure only one leader remains active. But if that mechanism misfires, you've taken down a healthy node. There are no clean solutions here. Every choice is a trade-off between speed of recovery, data durability, and safety.